Hi, in this video we'll be talking about the carbon basis of life. Now, you might be wondering how life could have sprung up from nothing. Well, there are actually two really good hypotheses for how these happen. The first was tested out by this guy named Stanley Miller, and it's sometimes called the prebiotic soup hypothesis. Basically, the idea was that back on the early Earth, the oceans had a lot of very small, basic organic compounds, and the Earth was being bombarded by lightning and other sources of energy, and this energy provided the fuel, so to speak, necessary to carry out various chemical reactions that converted those very simple organic compounds into the more complex organic compounds that are, well, essential to life. Now, one issue with this hypothesis is that, well, those organic compounds were just not very concentrated in the early oceans, and definitely not concentrated to the degree necessary to efficiently carry out a lot of these reactions. Now, another hypothesis sprung up when a particular hydrothermal vent field was discovered in the ocean. You see, back in the 70s, these hydrothermal vents called smokers were discovered, and these released, amongst other things, hydrogen sulfide. Now, there are living creatures at those vents, but it's a very, let's say, niche environment, and the life on planet Earth the diversity of life on planet Earth, that is, couldn't have arisen from organisms that sprung up at those vents. However, this other vent field, pictured right here, was discovered not that long ago, and these vents release methane and hydrogen. Now, methane, CH4, is about the simplest carbon molecule you can think of. And in addition to that, these vents form what are called chimneys, and inside of these chimneys you see here are very small passageways. So these passageways could have, in theory, concentrated the basic organic compounds necessary and allowed for these simple chemical reactions to occur. Now, what we do know for certain is that hydrogen, carbon, nitrogen, and oxygen are the basic components needed to make pretty much all the organic molecules necessary for life. Now, the most basic type of molecules amongst all of these are hydrocarbons, and hydrocarbons are molecules that are made exclusively of hydrogen and carbon. So again, the simplest form of these is methane, pictured above, a one carbon molecule. Now, hydrocarbons can have a lot of variety. And one way we can have variety with hydrocarbons is, well, by adding additional carbons. So let's say we take that methane and we add 2 more carbons, then we'd get this structure pictured above here called propane. You might have heard of this. It's commonly used as a fuel for, amongst other things, barbecues. Now, this 4-carbon chain over here is butane. This is the fuel commonly used in, amongst other things, lighters. Now, another way that we can see diversity in hydrocarbons is by branching our chains. What do I mean by that? Well, with methane, propane, and butane, we're just adding the carbons on in a line, like this butane here. But over here we have isobutane, and isobutane branches the four-carbon structure, like this. So again, these two molecules have the same number of carbons and hydrogens, but they're arranged differently. Another way we can see variety in hydrocarbons is with double bonds. Double bonds can be inserted anywhere really in a hydrocarbon structure and cause diversity. So in this structure here, we see that there's a double bond between these two carbons. This would be considered the first and second carbons of the chain. Now over here, we see that our double bond is now between the second and third carbons of the chain, and so on and so forth. As you can imagine, when you combine double bonds with branching and chain length, there's huge amounts of possibility for molecules you can make simply with carbon and hydrogen. Now, one last way that we can get diversity in our hydrocarbons is with ring formation. You see, this structure down here is a 6-carbon molecule. But instead of being in a straight chain form like this, we see that this carbon has a cyclic structure. Now, this ring over here has double bonds inserted into it, and this structure should look familiar to you. I mean, it's on my shirt. This is benzene. And you don't need to know the name of that molecule, but I figured I'd tell you since, well, you're going to be seeing a lot of it throughout this course. Alright, let's turn the page.